In this video, we're going to look at something called conditional probability. These are going to be some more complex probability problems, but with the same basis as we've done before. So we're going to use this thing called conditional probability to focus on one or two groups rather than the entire sample space. We're going to understand the relationship between intersections of events and products of probabilities with something called the product rule. And we're going to use tree diagrams to combine probabilities. So first, let's look at this motivating example. In a newspaper poll concerning violence on TV, 600 people are asked, "What is your opinion on the amount of violence on TV? Is there too much violence? Yes, no, or I don't know." And the responses are given below. And note that the responses are broken up between what men say and what women say. And then total, what's going on. So let's just answer some basic probability questions, and then we'll get into the more complex ones with this idea of conditional probability. So first of all, what is the probability that a person responded no? Well, let's look at the total. It's going to be the total amount of respondents, right? And then the number that say no. So total, there are 600. And the amount that say no is this box right here. 140 said no. So 140 over 600. What is the probability that a respondent was a man? Again, we're going to go over the total, which is going to be 600, and the probability of a man, or the number of respondents that are men, is going to be over 600. We're looking at the total number of men here, which is 280. So 280 over 600. So this is just kind of understanding how this chart works and how to do some basic probabilities. So now let's look at the more difficult question. What is the probability that a woman responded yes? Here we're kind of doing two things at the same time. We're not just talking about just women or just yes. We're talking about women that responded yes. So what we're going to do is we're going to kind of simplify this table. We're just going to look at just women because that's all that we really care about. And we're still going to think about the total here. And we're going to say the number that said yes. But everything here is in terms of just women. That's our entire sample space at the moment. So the total here is 320. And the number that said yes in here is going to be 256. So this is the probability that a woman responded yes. We look at just women total, and then how many said yes. So this is our idea of conditional probability. We're going to talk about this for a few more slides. So to make this problem a little bit easier, let's just talk about this notation. I'll call W the event that a respondent was a woman, Y be the event that a response was yes, and then the other ones as well. I think we're only going to use W and Y, really. So let's reword this question. What is the probability that a woman responded yes? We're going to reword that to, what is the probability that a response was yes, given that the respondent was a woman? And this is the key word we want to look on, given that. And this question we're going to denote with this notation, P, Y with this vertical bar, W, and that vertical bar is what we're going to call given that. So again, this is the probability that a response was yes, probability of Y, given that the respondent was a W, or a woman, W. So we found that this was 256 out of 320 on the previous page. But note that how we actually found that was we changed the denominator to be this N of W, how many women there are total. And the top was not the total number of yes, but the total number of yes and women. And this is our idea of conditional probability. So let's introduce it formally. A conditional probability is a probability whose sample space has been limited to only those outcomes that fulfill a certain condition. So in the previous example, we looked at just women. That's how we limited the sample space, not all people, just women. The conditional probability that event A given B is probability of A, this bar, which is given that B, is the number of things in the intersection, A intersect B, over the number of things in the limited sample space, B. So I think the big thing to think about for conditional probabilities is we can think about conditional probabilities as changing the denominator in the problems. We're no longer looking at all of the sample space S, we're looking at a small section of it, and we're kind of reducing the top and the bottom to only look at a small fragment of the population. So looking at this same example, let's answer some more questions about this given that, this conditional probability. So what is the probability that a response was yes, given that the response is from a man? So first of all, let's actually put this in the notation. This is the probability of yes, given that the response was from a man. What we're going to do is we're going to look at just men. That's what we're limiting this sample space to. So it's like this was the only information we were given, right? That's all we really care about. Note that the formula, this is going to be the probability of y intersect m, sorry, not probability, the number of y intersect m over the number of m. So the total number of men are going to be 280. And the total number of people that said yes and are men is this box right here. And that's going to be the 162. So total 162 over 280, we could reduce that if we want. That's not the purpose of this problem though. So similarly, but different, we can think about what's the probability that the response is from a man given that the response is yes. So that's the opposite direction, m given that y. This is the number of people in the intersection, and that's going to be the same. But now we're looking at just yeses. So here we're looking at this column, and this is like everything we have. So the intersection is still the same. That's still 162. But now the number of things total, there are 418 total yeses. And we're now saying that out of the total yeses, 162 of them were men. So these give us more information about these probabilities, kind of looking at just a subsection of the sample space. All right, a third question, which is different than the first two. What is the probability that a response is yes and is from a man? This is not a conditional probability. This is just the probability of m intersect y. We've actually done that a few times. Right, this is going to be the number of things in m intersect y over the entire sample space. So that's going to be our 162, which we've found each time, but this time over 600. So here's why I like to say we can think of conditional probabilities as changing the denominators in the problem. Let's look at this example. We have the same numerator in all of them, but it's the denominator that we've changed, 280, 418, 600. All right, the numerator can change with conditional probabilities, but it's really the denominator that we're focusing on, is that we're limiting it to different parts of the population. So with this in mind, now we can talk about something called the product rule. And the product rule is really just going to be a manipulation of this conditional probability. So let's look at this example. Using a standard 52 card playing deck, what is the probability that 2 cards drawn from the deck are both hearts? Note that there are 13 hearts in the deck out of 52 cards. It's 1/4 of the cards. It should be fairly clear that the probability that the first card we draw as a heart is 13 out of 52. There are 52 cards total, 13 of them are hearts. That's our probability. However, to find the probability of the second card, it's a little bit more complicated because we've gotten rid of one of the cards. So now there are only 51 cards in the deck, and there's only 12 hearts because we took one of them out. So the probability here is going to be 12 over 51. So that's our answer we have. We already gotten it, and we could probably do that before this idea of conditional probability. But let's think about it in terms of conditional probabilities. The probability that we had both hearts, we could think about as the probability that the first card is hearts times the probability that the second card is hearts. Another way to say that is the probability that the first card is hearts times not necessarily the second card is hearts, but that the probability the second is hearts given that the first card is a heart. That is our conditional probability. So this will be the probability that they're both hearts is the probability that the first is heart intersect the second is heart is equal to the probability that the first is heart times the probability that the second is heart given that the first is a heart. And what we're really doing here is we're saying the probability that both A and B occur is the probability of A intersect B is the probability of A given B times the probability of B. And this is really a manipulation of the probability of A given B is the number of A intersect B over the number of B. We multiply by the number of B on both sides. And you think about this as over N over S total. Then these become probabilities. This is really just equal to the probability of A intersect B over the probability of B. It's really just a manipulation of this conditional probability definition we gave on the previous page. All right, so how can we use this with more than just this example? We're going to use tree diagrams to kind of help with this idea of product rule. So still with this same example, let's look at the probability that both cards dealt from a deck are hearts. We're going to use a tree diagram. So we're going to start here by our first card has 2 options. It is either a heart or not a heart. And the probability that it is a heart is 13 out of 52. So the probability that it is not a heart is going to be 1 minus that, which is going to be 39 over 52. So then, at that point, we now are going to draw our second card. And we have 2 options, right? We have a heart or not a heart. Heart, not heart. And we said that the probability that it is a heart, the second card, is going to be 12 over 51. The probability that it is not going to be a heart is we still have over 51 now. There's 51 cards, but 39 of them are not hearts. This is also note 1 minus 12 over 51. On the other branch, if we did not draw a heart the first time, then this is the probability that we have a heart is going to be 13 out of 51. And the probability of not a heart is going to be 38 out of 51. Note that's 1 minus 13 over 51, as there's only 38 not hearts left in the deck. So what this gives is 4 different kind of probabilities here. We'll go over each of those in a little bit. The first one is what we just did. That's going to be the probability that we have the first is a heart and the second is a heart. And we know that to be the probability that the first is a heart times the probability that the second is a heart, given that the first is a heart. That's what we calculated on the previous page. The next line is the probability that the first is a heart and the second is not a heart. And that'll be a similar conditional probability. The probability that the first is a heart times the probability that the second is a heart, second is not a heart, given that the first is a heart. And the other two are going to be the probability that the first is not a heart intersect the second is a heart, which is the probability that the first is not a heart, times the probability that the second is a heart, given that the first is not a heart. And lastly, we'll finish it out, probability that the first is not a heart intersect the second is not a heart, which is going to be the probability that the first is not a heart, times the probability that the second is not a heart, given that the first is not a heart. So these probabilities, how we get them, are just by multiplying each step of the way. So if we go heart and then heart, this branch, we get 13 out of 52 times 12 over 51. If we go heart and then not heart, we get 13 over 52 times 39 over 51, and that's our probability. If we do not heart and then heart, that is 39 over 52 times 13 over 51. And finally, we could do not heart followed by a not heart, which is 39 over 52 times 38 over 51. So 4 different probabilities we can get here looking at different conditional things. So how does this tree diagram help us? Just kind of some basic properties of these. The non-conditional probabilities are the beginning of the tree. That's like the probability of the first being a heart. It doesn't depend on anything else. There's no extra condition. The conditional probabilities start at the given condition. So that the first is a heart, given the first is a heart, what's probably the second is a heart. All of those are the second line down, or whenever those conditions start in our tree diagram. When we want to find the probability of each branch, we multiply across the branch, as we showed. And then if you want to look at multiple different things, you could add different branches together. We'll see an example of that in a little bit. All right, so here we go. Use this tree diagram, we'll go back to it, and mutual exclusivity rule to find the probability the second card dealt from a deck is a heart. This is a different question than what we did before. This is, what is the probability that the second card is a heart? In fact, we never actually did this. We always did given that the first card is a heart. But note that we could write this as the probability that the second card is a heart and the first card is a heart, plus the probability that the second card is a heart and the first card is not a heart. There's kind of two choices to get a second card being a heart. Let's look at the tree diagram to show how this works. So to show that the second card is a heart, there are two options there. We have this branch and this branch. We could either draw a heart at the beginning or not draw a heart. And we're going to add those two probabilities together. So this is going to give us, this guy was 13 over 52 times 12 over 51. And this guy is going to be probability of the second is a heart and first not a heart. Go back to it. We're looking at this calculation here. 39 over 52 times 13 over 51. And this is our probability that we could simplify there. The mutual exclusivity rule is saying that these two events are mutually exclusive. They can't happen at the same time. So the probability of their union is just the probability of one plus the probability of the other. Usually we have to subtract off the intersection, but we don't have to worry about that here because the intersection is empty. All right, and that's going to be the case with these tree diagrams. That's always going to be the case here. All right, moving on from hearts and cards, let's talk about a completely different example. Big Fun Bicycle manufactures its products at two plants, one in Korea and one in Peoria, Illinois. The Korea plant manufactures 60% of the bicycles total, 4% of the Korean bicycles are defective, and 5% of the Peorian bicycles are defective. Draw a tree diagram that shows this information. So first, our first branch is going to be what plant we're at. Are we in the Korean plant or the Peorian plant? And we know that 60% of the bikes come from the Korean plants. That means that 40% come from the Peoria plant. Then we talk about defective versus not defective. So defective and not defective. Defective and not defective. The percentage that are defective in the Korean plant are 4%, which means that the ones that are not defective is 100 minus that, 96%. For the Peorian plant, it's going to be 5% and 95%. So here we think about our four different probabilities we're going to find. We're going to multiply across the branch. So here we have the Korean probability of Korean intersect defective is going to be 60% times 4%. The probability of Korean and not defective is going to be 60% times 96%. The probability of the Peoria plant being defective is going to be 40% times the 5%. And finally, we could do the probability of Peoria plant and not defective is going to be 40% times 95%. Remember, you have to use the decimal forms always for these percentages. All right, so here's our tree diagram. Now we can answer these questions very quickly with this information. Find the probability that the bike is defective and came from Korea. So note that that is going to be the probability of K intersect defective. That's our 0.6 times 0.04. Find the probability that a bike is defective. So that's going to be the probability that of defective is going to be the probability that it's going to be Korean and defective plus the probability that's going to be Peorian and defective. We're going to add together our two defective parts of our tree diagram. So that's going to be 0.6 times 0.04 plus the 0.4 times 0.05. And then find the probability that a bike is defect-free. We could add them up in a similar way, or we could use the complement rule. It's going to be 1 minus the probability of defective. So 1 minus that answer. All right, and let's look at one more example here. The batting averages for two pro baseball players, Derek Jeter and David Justice, over a time span of 2 years are given below. So we have how many hits they got out of a total number of at-bats in 1995 and 1996. Who had the higher batting average in 1995? So, first of all, let's look at just 1995. We have Jeter is 12 over 48, which is 0.250. And David Justice is 104 over 411, which is going to be 0.253. So the answer is David Justice's is higher. Who had the higher probability in 1996? Jeter had 183 over 582. That's going to be about 0.314. And Justice had 45 over 140, which is about 0.321. So which one's higher? David Justice again. So who had the higher batting average over the 1995-1996 time span? What we're going to do is we're going to look at the total number of at-bats, in which there are for Jeter 48 plus 582, and we're going to have 12 plus 183 hits. And that's going to give us about 0.310. For Justice, we're going to have 104 plus 45 on the top, 411 plus 140 on the bottom, which is going to give us about 270. So who had the higher average over both time spans? Derek Jeter did. So to answer the question, according to this data, who was the better hitter? And this is not an easy question. In fact, it doesn't really have an answer. This is kind of subjective as well. But David Justice was the better hitter in both seasons. In 1995, he was the better hitter. In 1996, he was the better hitter. But when you look at over both seasons together, Derek Jeter was the better hitter. And this is weird. This is a paradox here. How could he be worse in both seasons, but then be better overall? And this is actually what's known as Simpson's paradox. And we can talk about why it's true as well. So the reason why this works is because David Justice, so they both had a low number of at-bats in different seasons. And in 1995, the low number of at-bats corresponded to the low average. So it's like Derek Jeter had most of his really good at-bats in 1996 when he had the better average. David Justice had most of his good at-bats when he had the lower average, or most of his at-bats when he had the lower average. So when you put them both together, Derek Jeter's wins out. And this is something that happens all the time in different surveys and data collection kind of things, this idea of Simpson's paradox. We're not going to talk about it much more than that, just know that it's there, and this idea of reading graphs and trying to come up with a critical thinking kind of who's better. And again, there's no right answer to who's the better hitter, right? It's just, can you take the information and can you make a conclusion based on that? You could say that Justice was the better hitter for whatever reasons, Jeter was the better hitter, and maybe you could bring in more information to help defend those ideas.